Imagine you're on a ship in the middle of the Atlantic and it's sinking. Water is pouring in from everywhere. Tiny cracks, loose rivets, 1,000 little failures happening all at once. Now, here's the thing about quantum computers. They've been sinking since the day we built them. Every single one. But in December 2023, a team at Harvard just figured out how to deploy lifeboats while the ship is still going down. And what they discovered might be the most important breakthrough in computing since the transistor. But before I explain why this matters, I need you to understand something that most tech coverage gets completely wrong. When you hear about quantum computers in the news, you probably picture this incredible machine that's going to crack encryption, simulate molecules, and solve problems classical computers never could. And yes, that's the promise. But here's the dirty secret the industry doesn't like to talk about. Every quantum computer we've ever built is essentially broken. Not broken like your laptop when it freezes. Broken in a much more fundamental way. See, a classical computer stores information in bits, zeros, and ones. And those bits are stable. You can write a zero into memory, go make coffee, come back, and that zero is still there. Easy. But quantum computers use qubits, and qubits are made of the most delicate stuff in the universe, the quantum states of subatomic particles. And here's the problem. These quantum states are absurdly fragile. I'm talking microseconds of useful life. A stray photon hits your qubit, gone. Temperature fluctuates by a fraction of a degree, gone. Electromagnetic interference from across the room, gone. Your qubit doesn't just lose information, it becomes information garbage. This is what physicists call decoherence, and it's been quantum computing's original sin since Richard Feynman first proposed the idea in 1982. We've known about this problem for over 40 years. And for 40 years, the best solution we had was, essentially, make the qubits better and pray. Spoiler alert, that wasn't working. Let me put this in perspective. IBM, Google, they've been throwing billions of dollars at making individual qubits more stable. And they've made progress, don't get me wrong. But here's the math that keeps quantum researchers up at night. To run a useful quantum algorithm, something that could actually break encryption or design new drugs, you need to perform maybe 1 million operations on your qubits. 1 million. Current best case error rates? About 1 error per 1,000 operations. So you're running 1 million operations with a 1 in 1,000 error rate. That means you're accumulating roughly 1,000 errors by the time you're done. Your answer isn't just wrong, it's meaningless noise. It's like trying to solve a Rubik's Cube, where every 10th move you make randomly scrambles 3 other squares. You're not going to solve anything. You're just making expensive chaos. So here's where the story gets interesting. Back in 1995, a mathematician named Peter Shor, yes, the same Shor who invented the algorithm that could break encryption, proposed something radical. What if, instead of making qubits more stable, we made them redundant? This is where the lifeboat analogy comes in, and I want you to really picture this. You're on that sinking ship, remember? Water's coming in from everywhere. Now, you could try to patch every single leak. That's the make qubits better approach. Or you could do something clever. You could put your passengers in lifeboats and design those lifeboats so that even if some of them take on water, the passengers can detect the problem and transfer to safety before drowning. That's quantum error correction. Instead of storing your quantum information in a single fragile qubit, you spread it across multiple physical qubits in a special pattern. And here's the magic. Those qubits can check each other. If one starts to fail, the others can detect it and fix the problem, all without ever looking directly at the quantum information itself. Wait, why can't you look at it directly? Here's another quantum weirdness. The moment you measure a qubit to see what state it's in, you destroy the quantum information. Observation collapses the superposition. So you can't just check your qubits like you'd check memory in a classical computer. Error correction has to be sneaky. It has to check whether an error happened without ever learning what the actual quantum information is. It's like proofreading a document blindfolded, using only the sounds the words make when spoken aloud. This sounds impossible, right? But mathematically, it works. You can design what's called a logical qubit. That's your lifeboat, out of multiple physical qubits. And this logical qubit can detect certain types of errors and correct them automatically. The catch? It takes a lot of physical qubits to make one logical qubit. Previous approaches needed hundreds of physical qubits just to create a handful of logical qubits. Google, in 2023, demonstrated quantum error correction using 72 physical qubits to create just 2 logical qubits. 2. At that rate, a useful quantum computer would need millions of physical qubits. We're nowhere close to that. And this is exactly why what happened at Harvard in December 2023 made physicists lose their minds. Mikhail Lukin's team did something different. They didn't use superconducting circuits like Google and IBM. They used atoms, rubidium atoms, to be specific, floating in a vacuum, held in place by laser beams called optical tweezers. Picture using light itself as a pair of tweezers to grab individual atoms and arrange them like pieces on a chessboard. Now here's where it gets wild. With 280 physical qubits, 280 individual rubidium atoms, they created 48 logical qubits. Let that sink in. Google needed 72 physical qubits for 2 logical qubits. Harvard got 48 logical qubits from 280 physical qubits. That's roughly 6 physical qubits per logical qubit, compared to Google's 36:1 ratio. 6 times more efficient. That's not an incremental improvement. That's a paradigm shift. But wait, the number of logical qubits isn't even the important part. What matters is what they could do with them. Previous error correction experiments were basically demonstrations. Party tricks. You'd create a logical qubit, maybe do 1 or 2 operations on it, and then measure it before everything fell apart. It was proof of concept at best. The Harvard team? They ran actual quantum algorithms on their logical qubits. They performed 2-qubit entangling gates. That's the fundamental operation that makes quantum computing powerful, with error rates below the fault-tolerant threshold. Okay, I just used a term I need to explain, fault-tolerant threshold. This is the holy grail number in quantum computing. Remember the threshold theorem I mentioned? It states that if your error rate is below a certain threshold, you can perform arbitrarily long quantum computations. Below that threshold, errors don't accumulate faster than you can correct them. Above that threshold, your computer drowns in errors no matter what you do. The Harvard experiment got below that threshold. Not by a hair. They achieved 99.5% fidelity on single qubit operations on their logical qubits. That's not just good. For the first time, that's good enough. Let me tell you why this is different from every quantum breakthrough headline you've seen before. Every few months, some company announces they've added more qubits. IBM has 1,000 qubits now. Google has 72. These headlines are basically meaningless because they're counting physical qubits, those fragile, error-prone particles that can't actually do useful computation. It's like bragging about how many leaky buckets you have on a sinking ship. More buckets doesn't help if they all have holes in them. What matters is logical qubits, the lifeboats, and whether those lifeboats can actually keep your computation afloat long enough to finish the voyage. The Harvard result is the first time anyone's shown that you can build enough functional lifeboats efficiently enough to actually matter. Now, let me address something you might be wondering. Why are neutral atoms better than superconducting circuits? Why did Harvard succeed where Google and IBM have struggled? 2 reasons, and they're both fascinating. First, superconducting qubits need to be kept at temperatures colder than outer space. We're talking about 15 millikelvin. That's 15 thousandths of a degree above absolute zero. They need massive dilution refrigerators the size of chandeliers, consuming enormous amounts of energy and requiring exotic materials. Neutral atom systems? The atoms themselves are essentially at room temperature. They're trapped by lasers, not by extreme cold. The whole system is simpler, cheaper, and more scalable. You can fit more atoms in a smaller space without worrying about the nightmare of keeping everything impossibly cold. Second reason, connectivity. In superconducting systems, each qubit can only talk to its neighbors. If qubit A needs to interact with qubit C, it has to go through qubit B. This creates bottlenecks and limits what kinds of operations you can perform efficiently. With optical tweezers, you can literally pick up an atom and move it next to any other atom in the array. It's like the difference between a telephone network, where every call has to go through a switchboard versus just handing someone a note directly. The atoms can be dynamically rearranged to perform whatever operation you need. This flexibility is why Lukin's team could achieve such efficient error correction. Their logical qubits could be built using the optimal geometry for each situation, not constrained by fixed hardware layouts. Now let's talk about what this actually means for the future, because I know that's what you're really wondering. Qubit computing, that's the Boston startup spun out of Harvard and MIT that's commercializing this technology, is already talking about scaling up. They're not starting from scratch. They're building on a technique that's now proven to work. The path from 48 logical qubits to hundreds, even thousands, is no longer theoretical. It's an engineering problem now. And engineering problems get solved with time and money, both of which are flooding into this space. But let's be real about the timeline. Useful fault-tolerant quantum computers probably aren't arriving in 2024 or 2025. There's still work to do on increasing coherence times, improving gate fidelities even further, and scaling up the number of atoms that can be controlled simultaneously. The optimistic estimates from researchers in this field Maybe 5 to 10 years for the first quantum computers that can do things classical computers genuinely cannot. That's for problems like simulating molecular interactions for drug discovery or optimizing complex systems that are completely intractable today. The pessimistic estimates? Maybe 15 to 20 years. Still within most of our lifetimes. Still transformative. What I want you to take away from this video is not quantum computers are coming tomorrow or quantum computers are overhyped and will never work. Both of those narratives are wrong. The real story is more nuanced and honestly more interesting. Quantum computing has been stuck on a fundamental problem, error correction, for decades. And in December 2023, for the first time, a research team demonstrated that this problem can be solved efficiently. The ship is still sinking. The qubits are still fragile. But now we have lifeboats. And these lifeboats actually work. That's the breakthrough. Not more qubits. Not faster gates. The ability to preserve quantum information long enough to do something useful with it. John Preskill, who's basically one of the godfathers of quantum computing at Caltech, put it this way: we might be entering what he calls the early fault-tolerant era. Not the full fault-tolerant age where quantum computers solve everything, but the beginning of it. The part where we prove the concept works at scale and start building toward the real thing. This is like where classical computers were in the 1950s. The transistor had been invented. ENIAC existed. But the personal computer was still decades away. We're at that moment for quantum computing. The foundation has been laid. And here's the thing that doesn't get enough attention. This affects everything. Not just computing, but cryptography. The mathematical locks that protect every bank transaction, every government communication, every private message you've ever sent. Current encryption depends on math problems that quantum computers will eventually solve easily. When, not if, fault-tolerant quantum computers arrive, the security infrastructure of the entire digital world needs to be rebuilt. That transition takes years, maybe decades. The clock started ticking the moment this paper was published. Nations are already racing to develop quantum-resistant cryptography. China, the US, and Europe are pouring billions into quantum research. And it's not just for scientific prestige. It's because whoever controls this technology controls the future of information security. The Harvard result just told the world that the finish line isn't theoretical anymore. It's visible. Now I want to leave you with something to think about. The researchers who made this breakthrough, Mikhail Lukin and his team, they've been working on neutral atom quantum computing for over a decade. Not months, not years. Over a decade of failures, incremental progress, dead ends, and starting over. This is what real scientific progress looks like. Not the headlines, not the hype cycles, but a sustained effort by brilliant people solving one impossible problem after another until suddenly, almost without warning, everything changes. Quantum computing just got a lifeboat. And while the voyage ahead is still long, for the first time, we have real reason to believe we'll complete it. If this video helped you understand quantum error correction in a way that finally makes sense, hit that subscribe button and the notification bell. I break down complex science and technology news into stories you can actually follow without the hype and without the jargon. Next week, I'm covering another breakthrough that flew under the radar. Why a single experiment in 2024 might have finally proven that the many worlds interpretation of quantum mechanics is wrong. Yeah, that's the one where every decision creates a parallel universe. Turns out, we might actually be able to test it now. Click here to watch that video next, and I'll see you there.